Wave optics. In the previous chapter, ray optics, by assuming that light travels in a straight line, we easily explained the concepts of reflection, refraction, and dispersion. Now, the question is, does the light really travel in a straight line? Now, observe the illustration. Consider a light source illuminating a screen. If we place a coin in front of the light, the coin obstructs the path of light. If the light travels in a straight line, then we should see a dark circular spot on the screen. However, this does not happen. In fact, we get a bright spot in this place. This can only happen if the light bends at this point and reaches this spot. To explain the bending of light, in the year 1678, a Dutch physicist Christian Huygens proposed a theory called wave theory of light. When a stone is dropped into a stagnant water of a pond, waves spread out from the point of impact in concentric circles. Every concentric circle is associated with either a crest or a trough. If we consider any concentric circle, all points on the circle will oscillate with the same phase. This is because they are at same distance from the point of impact. A locus of all these points which oscillate in the same phase is called a wavefront. The speed at which the wavefront moves outwards is called speed of the wave. Now, draw a tangent at a point on the wavefront. Then, a line drawn perpendicular to the tangent at that point is called a ray. The ray is the direction along which the energy of the wave travels. Christian Huygens applied the same theory to the light and proposed that light travels in the form of waves. A point source generates spherical waves in 3 dimensions. Similarly, a line source like fluorescent tube and linear slits will generate wavefronts that are cylindrical in shape. A plane wavefront can be produced by any source located at far distances from the source. Best example is the plane waves which arrive from the sun. At large distances, a small portion of a spherical wavefront appears to be a plane wavefront. Now, if we know the shape of a wavefront at a time t is equal to 0, using Huygens principle, we can easily determine the shape and position of the wavefront at a later time. Let us consider a point source S. The source S generates a spherical wavefront AB traveling away from S. Now, according to Huygens principle, each point along the wavefront AB is the source of new disturbance, and spherical secondary waves originate from these points which spread out in the forward direction. These secondary waves are called as wavelets. If we assume that the medium is isotropic, then the velocity of wavelets will be same in all directions. The radius of secondary wavelets is given by r is equal to v into t. Now, if we draw a tangent to all these waves, we will get the position of the new wavefront A dash B dash. When time t is equal to 0, the radius of secondary wavelets will be equal to 0. It represents the initial position of the wave. When time t is equal to tau, the radius of the secondary wavelets will be equal to v into tau, and this will be the new position of the wave. In the similar manner, we can determine the shape of the wavefront of a plane wave going through a medium in forward direction. Unfortunately, there is one problem with this theory. Since the secondary wavelets are spherical, it will not only generate forward wavefront, it will also generate backward wavefront. But in practice, we do not find any back wave. To correct this problem, Huygens suggested that amplitude of secondary wavelets is maximum in the forward direction and zero in the backward direction. Later, Voigt and Kirchhoff mathematically proved that the amplitude of wavelets in any direction making an angle theta with the normal to the wavelet is proportional to 1 by 2 into 1 plus cos theta. Since theta for a back wave is 180 degree, the factor 1 by 2 into 1 plus cos theta will be equal to 0. That is why there is no back wave formed. Huygens' principle is also useful in explaining the phenomenon such as reflection and refraction of light. We will study about these in the upcoming videos.
If you shine a parallel rays of light on a cardboard with a tiny hole in between, what would you expect to happen to this light after it went through the hole? Well, if you think in terms of Newton's idea where light is a bullet, then we'll all see that these bullets will get blocked and these bullets will just go straight through. And this is the picture that gets painted. But careful experiments show that when the light goes through the hole, it actually spreads out and forms a bigger spot if there was a screen over here. How do you explain that? How does light just bend like that? Well, if you think of light as a wave and use Huygens' principle, then we'll be able to explain this. And that's pretty much what we want to do in this video. So we want to introduce this idea of Huygens' principle. But before I do that, let's do a quick recap of what we've already seen before. Huygens assumed that light is a wave in the ether medium that exists everywhere in the universe. And the ripples that these things are carrying, we give a name to that. These ripples are called wavefronts. And one of the important things that we saw about the wavefronts is that the angle between the direction on which the light is traveling, the rays of light, and the wavefronts, that is always perpendicular. Look at this. The rays of light and the wavefronts at every point will be perpendicular to each other. That's important. That's going to be important for this video as well. And this will be true even if you go very, 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 very far away. You will now see that the rays of light are pretty much parallel to each other. But if you look at the wavefronts, notice the rays are perpendicular to the wavefront. Rays of light always perpendicular to the wavefront. Okay, but how does this wave theory explain our original question? For that, we need one more piece of information from Huygens. How do these wavefronts evolve in time? Here's what I mean. Let's say we have a light bulb giving us light, and let's concentrate on one of its spherical wavefront. This is what it looks like right now. I want to know what this wavefront is going to look like, say 2 minutes later. How do I figure that out? Now at first, it might look like a silly question. You might think, or at least I should think, that that's easy, right? A little later, this new wavefront is just going to be a bigger version of our old wavefront, right? Isn't that the solution? Well, yeah, that's true over here. It works, but this only works provided there are no obstacles over here. But what if there is a mirror, or there is a lens somewhere over here, or if there is a cardboard with a small hole in that? Then what the new wavefront looks like? That's not so easy to answer now, is it? And this is why people went to Huygens and said, hey, Huygens, tell us, if I know what the new current wavefront looks like, how do I know what the new wavefront is going to be sometime later in general, in any situation? And that's basically what Huygens' principle is all about. It's going to help us reconstruct wavefronts. So what does the principle say? Well, according to Huygens, every single point on this wavefront is an ether particle which is oscillating pretty much with the same frequency as the original wave, and it starts producing its own spherical mini waves. So here's what it says. Remember that there is ether particle everywhere, and the ether particles on this wavefront, they're all oscillating. They're all moving back and forth as we saw in the animation. And as a result, he says that every single one of them is going to produce its own mini ripples, own mini waves. He calls them secondary waves. So this is going to produce its own secondary wave. This is going to produce its own secondary waves. So all of them are going to produce their own secondary waves. Now, since it's a little hard to draw, I've already drawn it nicely. So this is what it would look like. And you have to draw that for all of them. And there are infinitely many, because every point he asks us to assume it to be a particle oscillating and producing its own secondary wave. So these are all our secondary waves. And then he says, you draw a common tangent to all these secondary waves, a common envelope. So if I use a different color to do that, a common envelope, which might look somewhat like this common envelope, according to him, a common tangent, that represents the new wavefront. So he says this is a new wavefront. Again, let me show you an animation so you can see it better. So here's our current wavefront. And these are the ether particles which are going to oscillate and act like a point source, giving out secondary waves. I've not drawn all of them. There are infinite as many, okay? And notice these secondary waves keep expanding, keep expanding, keep expanding. And a common tangent to all of them, that now represents a new wavefront. So if I draw a common tangent over here, that common tangent would be our new wavefront. And the same thing would hold true for some other shape as well. So if I take, let's say, a plane wavefront, again, these are our ether particles oscillating and they're giving out secondary waves. And notice if the waves are going towards the right, this now common tangent will represent our new wavefront. So this method works for any shape of our wavefronts. The particles will always give you spherical ripples, and the common tangent will give us the new wavefront. And if you're now a little bit curious, you might have some questions like, why are we drawing the common tangent only on one side? Why not on the other side, for example? Well, Huygens would say, well, because we know in which direction the waves are traveling. We know the waves are not traveling backwards, so we will ignore them. But you could ask why. And Huygens doesn't have an answer for that, and that's one of the drawbacks over here. But you could have more fundamental questions like, why does this method even work? I mean, why are we drawing a common tangent? Why does that work? These are some great questions which we can try to tackle in a separate video altogether. But remember, just like any scientific theory, Huygens' theory is also not a perfect picture or representation of the world. Then why do we use it? Because it's simple and it's pretty powerful. As we will see, it will be able to explain a lot of phenomena, including deriving the laws of reflection and refraction in the future. Anyways, let's come back to our original question and see if we can answer that using Huygens' principle. So we were shining light on a cardboard, apparently a blue cardboard, and we want to know why does the light bend? That is our question, right? So let's use wave theory, Huygens' principle. Well, since the rays of light are parallel, our wavefronts are going to be plane wavefronts. So it's going to look somewhat like this. It's not a line, it's supposed to be a plane. And if I want to know what the new wavefront looks like after some time, I have to use Huygens' theory. But until here, I know the wavefront is going to look just like this, because there are no obstacles. I don't need Huygens' theory till here. But once I reach here, now comes the question, what does the new wavefront look like after this? Is it just going to be like this? Is it going to be this way? Let's find out. For that, we need to think of every single point on this as a source for secondary waves. We call these Huygens sources. And then we have to draw a common tangent to all those secondary waves. I want you to pause the video and see if you can give this a shot. All right, if you've tried, let's do this. So here are our Huygens sources. These are the ether particles which are oscillating, and they're going to start giving out their own ripples. So here's the ripples that I'm drawing. Here we go. And now what does the common tangent look like? Well, just like before, let me draw in white. Just like before, over here, the common tangent is going to look like this. But what's important now is that because this is a finite wavefront, there will be one last Huygens source over here, which will give you one last circular ripple over here, spherical ripple over here. And as a result, the tangent is not going to end here. It's not going to go straight like this, but it's going to end like this. This is what the new tangent looks like, and the same thing over here. Remember, we're drawing an envelope to all these secondary sources, and this is what the envelope looks like. And so notice that the new wavefront is not completely plain. It has this curved edges. And as a result, after this, it's just gonna be a larger version of this. So the new wavefront after this is gonna be, let me try and draw it nicely. It's gonna be like this. And again, like this. This is what the new wavefront is going to look like. And now if I try to draw the rays of light over here, the rays of light are going to be like this. They're always perpendicular, remember, to the wavefront. But over here, notice the rays of light have to be going this way, somewhat like this. And over here is going to be somewhat like this. And so there you go. Huygen's theory helps us understand why the light spreads out. Because when the wave exits this slit, it is no longer a plane wave. It gets curved towards the end, and as a result, it starts spreading out. This and some other phenomena of light can only be explained by thinking of light as waves and not as bullets. And this is how a wave theory gained popularity. All right, so to summarize, here are the two questions that you should try and answer yourself now. Can you explain Huygens principles to maybe a friend or maybe to someone in your family and explain how you construct new wavefronts from a given wavefront? And can you then use Huygens principle to explain why when you shine light through a tiny hole, it expands, the light tends to spread out? If you have difficulties, no worries, you can just go back and rewatch parts of the video.